Okay, so power factor, we will see the introduction and then we will see what is power factor and how to correct it. Relevant problem solving. By the way, power factor we can see from two different perspectives. One is the basics of power factors and another one is like if you look at the power factor from advanced power electronics side, we have to use different topologies. How can we make the power factor corrections? Because nowadays the modern technology is much more improved actually. So you can measure the power factor and you can correct the power factor in different ways. But today now we are going to discuss the basic power factor. So there are three possible loads. First one is resistive. Of course, we have studied, for example, in rectifiers or when we talk about the AC to AC voltage controllers, we talked about the circuit have only resistive load or it has only inductive load or the combination of resistive and inductive, and also capacitive load. So far, we haven't seen, at least in this course. So there are different possible loads, but three major loads are resistive, inductive, and capacitive. And of course, the combination of one or two or three is possible also. So whenever we have the resistive load to a circuit, what will happen? So here you can see this is the blue color is the voltage, red color is the current. So here you can see, so they are in phase. So it means there is no phase difference between the voltage and current. So current is in phase with the voltage. This is actually good. It means power factor is 1. But if you have inductive load, then what will happen? So here you can see this is the voltage. So here you can see voltage is the black color or dark blue, and then this IL current is this color. So you can see here the voltage and current, we have a 90-degree phase difference. So between this and this. So the current IL, this is the violet color, the current is always lagging 90-degree from the voltage. So that is the problem with inductive load. This is not okay. And similarly, capacitive load is the totally opposite to the inductive load. So here you can see the voltage is this dark blue and then this current is green color. So the current is, now you can see here current is leading 90-degree from the voltage. So there are three loads and each load have a different property. So there is a phase difference between voltage and current. So real-time loads, when we consider, most of the industrial loads can be considered as the combination of resistive and inductive loads. So R and L. That is why in the problems, when we discussed about converter circuits, we had seen R load and RL load. So current always lags voltage by some angle, except in total resistive loads. Of course, if you have total resistive load, then no problems. But in practical, it's not possible. We always have some inductor or inductance property in the load. So we have to find this angle, the angle between the current and voltage, and keep it under control. That is why we are talking about the topic called power factor. This power factor is a measure to identify the angle and keep under control the angle between voltage and current flowing in the circuit. So now we have to know three different terms, that is true power, reactive power, and apparent power. So true power means it's the actual amount of power being used or dissipated in the circuit. So it means the load is consuming only this one, that is called a true power. We can use this kind of notation, TP or P for true power. And it's a function of circuit's resistance. Let's say here, TP is equal to I square R. This is the true power. And the reactive power means if the load has inductance or capacitance property, then we will have this reactive power. So it's the amount of absorbed power or returned power by the reactive loads. For example, when we talked about the rectifiers with the inductive load, I mentioned that the inductor is storing the energy, and then even though after the positive cycle goes to zero, then the inductor will still supply the current in the opposite direction. So that is called reactive power. So it's a function of the circuit's reactance. So if the circuit has inductor in the load, then that is inductive reactance. If it has capacitor, then capacitive reactance. Or if it has both, then we have to consider both inductive reactance and capacitive reactance. This is also Rp is equal to I square X. X is the reactance value. This is nothing but P is equal to I square R. The same basic formula we are using. Here R is the impedance or reactance. Normally it's a resistance actually. The I means that is the current flowing in the circuit. P is the power, where maybe because of the power dissipation in the resistor or power dissipation because of the inductor or capacitor. So that is why this is the power, but this is called a reactive power. I square times X. Apparent power means it's the combination of reactive power and true power. So we are adding these two, then we can get this true power and reactive, apparent power. It's a function of the circuit's impedance Z. So now you can see here, true power is in terms of resistance, reactive power is in terms of reactance. Here apparent power is in terms of impedance. It's all are different actually. So here the power is S is equal to I square S, I square Z. So everything is following this basic formula. So now if you make this kind of triangle, maybe you had seen in some open source materials as well. So this is called true power, the bottom line in kilowatts. This left side line is called reactive power in kVAR, and total power is here. That is the apparent power. So that is equal to, that is in kVA. So now this true power is the actual power consumed by the load, but we are applying, this is the total power we are applying. But instead of using the entire power we apply, the load is using only some portion of the power, and some of them are wasted in the because of the reactance in the circuit. So that's why we are going to calculate the power factor. How can we control this reactive power? So power factor formula is, simple formula is cos pi or cos theta is equal to true power divided by apparent power. Similarly, just before what we talked about, transformer utilization factor, output power divided by input power, right? So here the same, this is the output power, true power consumed by the load, and this is the total power we are applying. So now if you make this, what is the value of this apparent power? Apparent power or AP is equal to TP square plus RP square whole power 1/2. It means square root of TP square plus RP square. This is the formula for apparent power. Total power is equal to true power plus reactive power. And we are writing in terms of RMS now here. And power factor is a measure of efficient output divided by input. So the same logic we are using in so many factors calculation. So it's now we are calculating in terms of power factor. Output divided by input. So we also have some other formulas for power factor. So you can see here the same, I just write in this way. So true power, we have the reactive power, the total of true power plus reactive power, that is the apparent power, the total power. So we know the power equation, another formula for power, that is P is equal to VI cos pi, right? VI is the normal power, and when we consider the angle, then we are putting this cos pi. So now power factor is equal to cos pi is equal to P divided by VI. That is the equation. So here, this is one of the formulas for power factor, and we can also calculate the power factor is based on this one. So that is the true power divided by apparent power. So we know the unit of true power is kW, and apparent power is kVA. So kW divided by kVA. So in some references, you can also see this one. And also you can calculate this cos pi is equal to R by Z. So this is the resistant or resistive property of the load divided by the total impedance property of the load. So this is same like this, true power divided by apparent power, but we are writing in terms of resistance value. So there are several formulas you can use to calculate the power factor. And the apparent power, yeah, it is the same from the previous one. So what is power factor? It's a measure of how effectively the current is being converted into useful work output. So it means efficiency, and how efficiently we are using the source power, or yeah, that is the indicator. So this power factor is just an indicator of the effect of the load current on the efficiency of the supply system. So this is a typical analogy. If you just Google it, or you use the any open source, or you can find this kind of example. So when you just go and buy beer in the bar, you will get like this. So you are paying the money only for the beer actually from here to here, but you are also getting more bubble actually. Of course, the bubble is not really, this is not you want to drink only this one. So I remember, like when I go with some friends, they are very insistive to the bartender, and they're asking to wait for a little bit so the bubble will go away, then they will just get little more beer. So this is, you can apply here actually. This is called the total power, let's say here, and this is the true power. This is what you are going to consume, but you are also getting this kind of bubbles, unnecessary ones. This is what happening in the load. So you are applying, maybe for example, you are applying like 100 kilowatts, and the load is using only 80 kilowatts, and the 20 kilowatts is wasted by the reactance of the load. So the efficiency is what? So you are applying 100 watts and you are using only 80 watts, and the 20 watts got wasted because of the reactance. These 20 watts waste, or the energy loss, must be reduced. That is our goal. So that in the, of course, in the industry, we are using something called power factor to address this problem. So here the same, this is the active power or true power, and the reactive power, this total is the, yeah, the total power. That is the apparent power. So how can we improve the power factor? So you can use, of course, the correct sized motor according to the application, or whenever you do not use, then you can just shut down the motor, just like how the PC is doing automatically. It goes to the power saving mode, but there is no such a thing for motors. Yes, nowadays it's possible also in some ways, but not exactly like what computer is doing. And also the third method is you can add a capacitor in the circuit. So the capacitor will also help you to improve the power factor. Of course, we are not going to see these first two things. These are practical things, and we will see this installing a capacitor. So here you can see normally it's like this. We have the true power, we have the reactive power, and we have the apparent power. And now what will happen? Now this is the circuit. Normally the circuit has the load, it has the resistor and inductor, or resistive property and inductive property. Now I am adding the capacitor. So normally this, because of this before I add the capacitor, what is going on here? You can see here the angle pi 1, that is the power factor. It's you can see here, and the current is lagging too much from the voltage. But because of adding the capacitor, I'm reducing this angle. It means I'm improving the power factor. So you can see here the kVA is moved towards upwards from the lagging. It's getting more close to the true power. So this is what we want. The formulas, again, I am repeating in all the slides. So there are different formulas to calculate the power factor.